Hello and welcome to the Rethink Energy CSP webinar. I'm Andries Wantenaar, the author of our recent CSP report, which you can buy from our website for a bit over $2,000. And this webinar is going to consist of mostly pre-recorded videos. So the first one is me discussing some main conclusions of the report, and then there's a few interviews that I've pre-recorded with some startup CEOs. We have one of them with us already. That's John Ingram. Hello, John.
Hello, good to see you again.
So we're going to play those videos. That'll last about 45 minutes. But we also have a Q&A session afterwards, because we've got John Ingram here to answer it. We should have Bruce Anderson of 247Solar here as well. Hopefully he'll turn up at some point. And so any and all questions you have, please type them in the chat. And to access that chat, you need to click on the show sidebar button in the bottom right of the screen, and then go to the questions tab to type in there. And there's also the chat as well if you want to talk there. So you can email me afterwards as well if you like. So do type those questions as soon as they occur to you, and we can ask them of Bruce Anderson and John Ingram. Hello, Bruce. Glad you could make it.
Hey. Hello. How are you today?
Fine, thanks. I was just introducing the platform, and so we're going to play these interviews for 45 minutes first, and then we'll do the Q&A session. So I think that just about covers it as far as the platform is concerned. So I'll just get cracking. Hello and welcome to the Concentrated Solar Power webinar. I'm Andries Wantenaar, the solar analyst for Rethink Energy. And at this point, it's undeniable that CSP has already begun its resurgence after a decade of total stagnation and even some failed projects. Because there have been projects commissioned in the last 2 years in about half a dozen different countries around the world. And that's using generation 2 technology, which is molten salt and parabolic trough, thermal oil, that kind of thing. And that will continue to be important, but we're also going to be covering generation 3 CSP, which is a lot more high powered than that. But anyway, let's start with China as an example. I'm choosing China because it's the biggest single market. It's also a place where I can talk about some recent news, and because it's mostly only reported in Chinese, I won't be boring you with it. You probably won't have heard of some of this. So it's now quite common in China to see multi-gigawatt wind and solar complexes announced in the northern deserts. And very often you will see some CSP or some batteries or some hydrogen announced alongside that. So this is a clear opportunity for CSP. Some of the projects that have already come online have been praised for enabling photovoltaics to participate on the grid consistently. They used to have a lot of curtailment out there because of the distances involved on the transmission grid. Some recent news, for example, I've got on the screen about 3 100 megawatt CSP plants being put out to tender in Qinghai province. And Qinghai province has a 3 gigawatt target for CSP in 2030. And there's 6 of those provinces in China which are suitable for CSP in terms of the natural conditions. One of them is Hebei province around Beijing. And of course, there's plenty of demand there, including industrial demand. And I've already mentioned hydrogen, but there's a lot of industry migrating north within China. So you can see how I think in the world, as we reach 45 gigawatts by 2030, I think the grid demand will continue to be the single biggest source. But I do think that the other 3 types, the microgrid, the hydrogen, and the industrial, I think that will become significant in the later part of the decade, and especially the 2030s. And obviously, dispatchable renewable energy is at its most valuable in grids that no longer have a huge amount of coal and gas, and in grids that have a lot of intermittent renewables. But I actually also think that even a place like Iran could have some renewables, because they will have Chinese investment. They will have, and the Chinese developers that have finally commissioned some of these pilot projects that the country commissioned, ordered to be built a few years back, those pilot projects have finally been completed. And so what China now has is it has a few CSP development companies that have a solid supply chain, that know what they're doing, they have experience, they have finance, and now they're expanding beyond China's borders into places like Thailand and Crete and Cyprus, so and Chile, of course, and the Middle East. So this 45 gigawatt figure is pretty certain, really. Spain has another 5 gigawatts that's more or less baked into the cake now because it's a government target. And Chile, I'm not sure if it has a specific government target yet, but what it has is just this incredible mining industry, incredibly hungry for electricity, best CSP resources on the planet. They're building lots of renewables, especially solar, so overnight energy storage will be immensely valuable there. And you also have the fact that hydrogen, the future of green hydrogen being mass produced from massive renewable energy complexes points towards definitely some CSP being built for those complexes to keep the electrolyzers running all the time. Now, some of the green hydrogen complexes will be running offshore wind south of China and in the North Sea, but most of them are going to be in the desert where you have good resources for solar, very cheap land, and that's places like Western Australia. Again, the Atacama Desert in Chile, I keep on mentioning it because it's just such a great place. Probably the Middle East as well, and northern China, like I've mentioned. Spain is another place. And then there's industry. Now, that's a little bit more limited, I think. You can't transmit heat for industrial purposes across the world like you can with hydrogen. But there are, again, some very suitable places that have both industry and good irradiation. By the way, this is a map of direct normal irradiation, courtesy of the Global Solar Atlas. And you've got California, you've got certain places in the Middle East, you've got, again, northern China. There's industrial migration taking place within China from the south that's more prosperous to the north. Spain, again, probably, I think Turkey will have some CSP, not much this decade, but it will do some. It's got great conditions. And but while we're looking at this map, you might think that it's only the yellow that's suitable for CSP, and probably this map is not a perfect guide, because I think places like Florida, probably not ideal for CSP, because while it has good average DNI, it probably has seasons where it has a lot of cloud cover. So this map isn't a perfect guide, but it does, there's even been a CSP plant suggested for Thailand, which is pale green here. So if they can do it in Thailand, they can and eventually will do it in Brazil and in Gujarat, place in India, places like that. So a lot more than you would expect, a lot more variety. And another thing to point out is that it's really not the same as batteries. The thermal storage that CSP brings to the table scales far more easily. It's not the main cost source. Batteries will run into issues with the easily available lithium being dug up already, and then a lot of that has to go to the EV market as well. And we've already seen 17-hour storage using molten salt, but that's going to be scaled to 48 hours, I'd expect. Well, that 48 hours is a figure I heard from a startup that wasn't willing to describe how they were planning to achieve that because they didn't want their idea stolen. But certainly we will go beyond 17 hours where it's relevant and useful to even do so. So it really cannot be compared to batteries. It definitely has a clearly defined niche apart from that. So we've got some more topics which are more important, actually, some very spicy stuff like the Generation 3 CSP that's 1,000 degrees. And LCOE declines are really the most fundamental. So we're going to speak to some CSP startup CEOs to go over those next. So that's just the introduction there. The first, I'm just noticing a question in the chat. Yeah, we'll be sharing the link to the recording, and I don't think it would be worth it having it as a PDF. But anyway, the first of our recordings with a CSP startup CEO is with Craig Wood, and he's from Australia, so he couldn't attend with us right now because it's It's 1 a.m. I think, so he's asleep. But he is the. I think I introduced him in this video, but he's the CEO of Vast Solar, which is, like I say in this.
So the next thing I wanted,
like I say in this, he's going to be building the first CSP plant that is not molten salt or thermal oil. It uses a different technology.
next thing I wanted to talk about was the variety of HGFs and the temperatures that are being seen in various of the startups that have sprung up. I mean, one of them I actually spoke to in I think it was Western Australia, was called Raygen, and their design was very unusual, probably not even entirely in the same category as the rest of CSP, but they decided to go with 90-degree hot water. And I think they were running an organic Rankine cycle, and because it was only 90 degrees, they actually can put satellite-grade photovoltaics at the receiver. So that's a very, I don't know how big that'll get, but it's certainly an example of how varied things will be. There's focal line solar in the Ukraine that we've spoken to, and they're going to do thermal oil parabolic, but they're actually going to use a cheaper form of oil and try to make everything else in their setup very cheap as well, and just do it at 300 degrees instead of 400. You've had atmospheric pressure out. We're also going to talk about that later as well. And you've got bauxite particles, you've got liquid metals. So a lot of different possible fluids and ways to transmit the heat. But for now, every commissioned project in the world is still just molten salt and thermal oil. Probably the very first company that's going to commission something different is Vast Solar, using liquid sodium at, I say 800 degrees on this, but I think you just told me it's actually 600 degrees that you're going to be operating at. Isn't that right? So if you want to seize control of the screen now and show me some of your slides, that would be much appreciated.
The difference in the system that we have developed is not in the generation. We're using just a standard Rankine cycle turbine. It's not in the storage. We're using a standard 2-tank hot and cold molten salt storage solution. Really, all of the difference in our system is out here in the collection. And the fundamental change that we've made is that if you think about a parabolic trough plant where you've got thermal oil, which is limited to 400 degrees, we've instead perfected the use of liquid sodium metal as a heat transfer fluid that replaces the thermal oil. Now, the sodium has a couple of very advantageous benefits, one of which is it has a very wide operating temperature range. So it freezes at about 97 Celsius and it boils at about 883 Celsius. Which means that there's an ideal temperature range with a large margin for error either side of what you need to operate to pass heat back into the molten salt system. And then the other benefit that's really critical is that the conductivity of liquid sodium is roughly 2 orders of magnitude higher than that of solar salt. And what that means is we're able to recover from a freeze if we have one in the solar field. And that's really critical. I mean, in our estimation, one of the major reasons why central tower receivers have all of the salt in one place is to manage that freeze risk, because if you have a freeze, it's really very difficult to recover. The great thing about liquid sodium is that if and indeed when we have freezes, it's very straightforward to recover. It's a matter of turning on the heat trace, or in the case of the receiver, just bathing the receiver in a modest amount of solar flux and letting time do its work, because the conductivity is so good that it actually unfreezes with a great degree of ease. So that's the essence of our system is using liquid sodium metal as the heat transfer fluid. The properties of the sodium, other than the operating temperature range and the thermal conductivity, we make some use of, and in particular, the high thermal conductivity means that we're able to have a smaller volume of fluid doing the work to remove the flux, which helps with controllability. But it's really, the fundamental benefit is really the ability to move to a modular solar array.
Great. And you were just telling me
the liquid sodium can operate at 800, but you take it down to 600 just for ease of use, really, because you're not changing the type of turbine that's being used to the supercritical type.
Yeah, so it's almost like the Goldilocks zone. If your process temperatures are too low, you end up with inefficient power cycles at the turbine, and that's really one of the fundamental limitations in our view of the parabolic troughs. I mean, don't get us wrong, troughs are a terrific technology, very bankable, very predictable, but the energy ends up being expensive because the turbine's quite inefficient. Once you get up to, our turbine inlet temperature of 538 Celsius, you start to be talking turbine efficiencies in the low 40%, and that's economic at that point. Yes, sodium can go hotter, and certainly we're involved in partnership with the Australian Solar Thermal Research Initiative, ASTRI, and CSIRO in developing some high temperature research projects. And so it's very possible to do that. But the challenge becomes that whilst the sodium's able to do it, and certainly receivers and heliostats and all that part of the system is relatively straightforward, at an industrial level, you start to run into either availability or cost challenges in terms of the other components in the system. Simple stuff like valves and seals and pumps. And those challenges only get more intense as you go to hotter and hotter temperatures. So, I guess you would say we are supercritical CO2 ready, in that we believe that sodium is the ideal front end for a supercritical CO2 turbine system. But in our estimation, it's a better business proposition right now to be focusing on rolling out CSP at 600 Celsius, give or take, with solar salts as the storage medium, whilst the development of the SCO2 and in particular the high temperature storage comes through and eventually will be deployed. But that isn't immediate in our estimation.
On the topic of the grid participation, I mean, you're off in northeastern Australia. I think the place you're building this Mount Isa project of 50 megawatts, it's not even connected to the national grid yet, is it?
No, that's correct. So Mount Isa, it's an isolated mini grid. There's about 400 megs of generation and about 330 megawatts of load. So it's not grid connected, and that's been one of the challenges and the opportunities that's informed the project that we've developed. So the project is, as you said, it's a 50 megawatt generation system. But in order to connect into that mini grid, any generator has to be able to supply energy that is continuous. So it's not good enough to simply have a PV plant with a battery, even if it is coupled to a CSP plant, because you do still get things, periods of time where there are clouds, you get bad weather days, and you also get things like turbine outages for maintenance, and you need to be able to cover those. And so the system that we're taking through to FID next year is actually a 4-generation system, a 4-technology hybrid, I should say, where all of the generators are dispatched to fulfill different roles. The CSP is configured to have 14.5 hours of thermal storage. So the thermal battery charges during the day and discharges at night. The PV provides daytime energy, but it needs to be firmed by a battery because PV's pretty ordinary when you're trying to achieve 99.5% reliability, as well as servicing a flat load. And then the main site is connected via a transmission line back to the original power station site that services the Mount Isa region, and we have a bank of gas engines located there. So those 4 assets actually are dispatched as one system to provide the high reliability solar baseload hybrid that actually allows us to provide energy to power underground mining and minerals processing operations.
And how do you see it, the balance within your hybrid plant changing if you're going to, if you were to do another one in a few years, which I guess you're planning on? Will the gas still be there? Will the PV and the batteries be smaller perhaps, or will it more or less stay the same?
Oh no, the mix of assets in the configuration is very much dependent on the situation. So that configuration that I just had up on screen is the sort of thing that you will build in an isolated situation where you actually have to provide firm energy. I think over time, as things like hydrogen technology matures and the costs come down, you will find that the gas is replaced by hydrogen. But that sort of configuration, I think, is going to persist for some time. If you move instead to look at what you would build on, say, in a grid situation, it would be quite different, because you would be relying, I think, on other assets and transmission and geographic dispersion to provide much more of that firming. And so I think you would, certainly you would be unlikely to have the gas assets, and you may well get away without the battery, depending on how strong the grid situation was. So it very much depends on the situation in which the assets are being deployed, as well as what the customer's needs are, as to the level of firmness that you need to build into the asset selection.
Do you have some more slides to talk about? Anything else you'd like to cover?
Let me just give you maybe a couple of sentences on the process heat thing. It's quite a natural fit that CSP in due course will become a primary energy source in applications where you need electricity and heat. Our strategy at the moment is to focus on utility scale electricity, because we think that's the easiest market to access, albeit it's trivial. And we think that that's also the quickest way to get things like our manufacturing technology, our manufacturing to scale, which will mean that technology becomes cheaper again. We are working with a major international business looking at deploying CSP to support some of their process heat requirements here in Australia, and there's a couple of other opportunities that they're looking at in various locations around the world. But what we are finding is that the technology choice in terms of the menu of CSP options that you can deploy is very much impacted by the temperatures and the requirements of each individual process. So putting CSP into those process heat applications is quite a bespoke activity, which means that it's relatively high cost. It's not, doesn't seem to us to be cookie cutterable, if indeed that's a word. We think that will change over time as solutions become more commoditized. And we also think that what will eventually happen is that there will be quite a fundamental reshaping of the way industry works, and in particular where industry is located, because as processes, for example, like green minerals refining come through to maturity, it will make sense to be doing those things where the cheap renewable energy lies. Now, that is not the world we live in today. At the moment, there are a small number of opportunities to apply process heat at scale in existing locations, but we certainly see the process heat opportunity becoming important over the 10 to 20 year horizon as the industry is reshaped, and also I think increasingly as the use of gas as a fossil-based fuel becomes less and less acceptable.
So that's the end of Craig Wood's interview. I'm seeing a question about his technology, which I think I can answer at the end, but sadly he's not with us today because he's in Australia, like I said. The next one is going to be from John Ingram, who is with us. And I didn't introduce him properly when I was recording this, so I'll just say a few words before I bring him on, bring his recording on. He is the CEO of a startup whose manufacturing is located in the Ukraine, because they have a lot of scientists working as taxi drivers, basically, so it's easy to employ them on the cheap. And but he's an American, and I think he's building his production line right now. But I think we covered that in the video, so I'll just put it on. So another important thing to cover for forecasting CSP over the next decade is where the LCOE, the levelized cost of electricity, is going to end up. And what I've done on this graph is quite simply I've applied Wrights Law. And Wrights Law is the idea that the bigger an industry gets, the more experience it has, the more stuff it deploys, well, the costs go down sort of in a predictable mathematical manner, just based on the scale and based on previous cost falls within that industry as its scale has grown. So that's what I've done with CSP, and you can see that I've got a utility scale photovoltaic line on here for comparison. So this graph is just really an extrapolation of the assumption I've made earlier, which is that global CSP capacity will go up from 6.5 gigawatts now to 44.5 gigawatts in 2030. So, but that's kind of a vague way to look at it. So I thought I'd bring on John Ingram. He's the CEO of Focal Line Solar. Hello, John.
Hello. Well, good to be with you.
And you have a startup in the Ukraine, which is kind of unusual because a lot of CSP technology, people are always talking about how it can be more powerful, more hot, more efficient, but you've actually gone the opposite direction. You've even decreased your target temperature to 300 degrees in a thermal oil parabolic trough approach. And you're really looking at how to make it all cost efficient and a lot cheaper. Could you talk us through your approach, and especially all the ways in which you plan to reduce the LCOE?
You've mentioned one of the greatest ones, right? We've chosen a temperature at which, below which things are really easy to do, and above which they become increasingly difficult. And you can just read difficult as costly. So, materials get more difficult. Storage certainly changes its nature from a sensible heat storage to molten, which we know is effective, if not cost friendly. One of the things we've done is really look at the hardware and how it's done, and that really comes down to the base collector itself, the parabolic trough in our case, as well as the receiver. And we've taken a radically different approach to the receiver, in which we reduce the cost to about 1/10 of a typical glass insulated vacuum sealed receiver. So that's one aspect. Our energy storage, which we almost always look at 12 hours minimum. And you want to do that, and not as a short picture, not as serving in an evening, but we look at it over levelizing through the year, so we can get better utilization of our turbines or whatever the downstream is. Because let's be honest, it's a very intermittent source. Even though it's quite predictable, it's up and it's down. And if you look at a distribution hour by hour over a year of solar installation, it's quite varied. The balance of system obviously goes along with that 300 in a way. So a lot of our components and so forth become cheaper and simpler as long as you control that temperature. And having chosen that temperature, coming back a little bit, it really has to do with applications, right? There are few applications, concrete, steel, and others, where you absolutely need those very high temperatures, and we're not looking at that market. And if you need those, then you're probably going to pay whatever the cost is. So setting those few applications aside, the thousands of applications which are left are quite applicable to 300C and less. So, doing our collector design as a factory built unit, which has very little assembly time in field, and high density shipping and so forth. So it really changes the nature of how we're shipping it and the installation. So you don't need a crane. This is man installed, and it's very rapid to install. So again, those are just different buckets: energy storage, balance of systems, shipping, logistic, installation. And then the last bucket being O&M, because once you've built it, you got to take care of it for 25 years.
So you're big. It sounds like the 300 degree approach. You view it as making a lot of things cheaper. So what would happen?
It has a trickle down effect, yes, as well as choosing 1,000 degrees has a trickle up effect. Right? But if you need 1,000, there's nothing you can do, right? You're going to have to go for a certain system and accept what it costs. So
if you were to convert your 300 degree thermal oil parabolic trough system to a more typical, I think, one thing you mentioned is that the 300 degree thermal oil is a different type of thermal oil, and it's cheaper.
That is true. That is true. It's non-synthetic. It's organic. It's not a synthetic, and that makes a huge difference as well, right? So at 350, you are already left with almost exclusively, synthetic oils at that point, and those are 10 to 20 times more expensive.
So, Mark, just talk us through some more of the other ways that you're going to reduce this LCOE on this graph.
Right. So what I wanted to say here, and you can see that, I'm representing some changes and some cost reductions as being minor and some as being quite significant. And this is all relative. So the main point is that, a lot of applications, especially those which are direct thermal applications, you're going to be looking for the cheapest heat source that you can find. And having high temperature isn't really going to benefit you because it's going to drive up your cost. And so what we're looking at here, and what I've tried to represent, is that this cost methods and these avenues we use to reduce cost, it's approximately going to bring the cost down by about half compared to a system which was really not optimized for that. And this is the cost of heat energy in this case. It's CST. Now, of course, you can convert that to electricity, and we certainly will be doing some of those applications as well. So, hardware being much cheaper, it's a lot of that does come down to the two main factors being factory assembled and being the labor is very cheap in that way because it's processing quite quickly, and using that different style of receiver, which isn't prone to breaking, and it's very high in performance as well.
And then you've got the energy storage. Is that just because it's a cheaper material that you're using?
It is a combination of several things. It's a very different approach. It has not been done before. It is cheaper materials. It's using less of certain materials, more of others. I really don't want to give that secret away, but I just kind of hint around the edges of it. And it's not a molten salt approach. It is not. It's most definitely not associated at all with those approaches. So we definitely benefit from, using very standard, commercially available anywhere in the world pieces. So it's a matter of the design and the operation of it as opposed to what it really is.
And your installation cost is one of the larger ones. Is that because you've got this assemble on site?
That's right, because it is non-assemble on site. It comes assembled, and the only thing we do is stick the receiver on it. So it comes very high density shipping, 40 units per container. They pop out, the time you pull it out of the container till it's sitting on its mount can be done in 15 minutes. So it's very fast. There no field alignment, it's factory aligned. So as composed, the IKEA model where it comes as an erector set and you have to put 1,000 people in a field putting these things together day and night, rain, snow, dust storms, whatnot. It's much different. It comes mostly completely assembled. You have to install the receiver, obviously, in the field, but that's quick and easy. So,
and I guess it's a sort of cascade effect where if you were using a more expensive design, then you would kind of be obligated to spend a lot of money then on manpower to make sure it's all perfectly aligned in the field. But with yours, because it's cheap to begin with, you can get away, in a sense, with losing some efficiency here and there.
We have taken that calculation into, as you say, there's the cost efficiency trade, and it exists everywhere, whether you take it or don't take it. And we definitely have considered that and made very small changes. So sometimes you can save a great deal of money by taking a very small efficiency hit. And we have done that in a couple of places. Installation isn't really one of them because we do the alignment in the factory. It is aligned. It's just aligned in the factory as opposed to in the field. And we can do that because our mirrors are set in the factory, whereas the mirrors and the frame and everything from our competitors in typical parabolic troughs, in fact, in all, is set in the field. When you assemble it, then you have to align it because previous to that, there was nothing really that could be aligned. So, part of the reason we can do it in a factory and assemble it is because it's not very large. It's not 5 meters across.
So your troughs are actually smaller in scale as well.
They are indeed.
And again, perhaps that's because that's made easier to be small because it's a lower temperature, or does that?
That's correct. right? Because you're not going to get to 450 with a smaller aperture trough. You just aren't. That's not the physics of it. So, but given that there are really so many applications that are hungry for 300C at a cost they can afford, 1 cent per kilowatt hour is a pretty decent heat cost. I mean, depending on your location. So, and a lot of people are looking for just heat.
So you actually are looking at supplying heat already, because something I hear from other CSP people is, oh, well, heat's kind of further in the future, especially the 1,000-degree stuff. We just want to be providing electricity and storage on the grid. So,
well, that's all well and good, and the market is there and ready and huge. Let's be frank, but heat is low-hanging fruit in many cases for many applications. There are quite a large number of applications requiring heat in pretty decent scale. So, why not? If it's there and somebody's ready to do it, why wouldn't you? It's an easier application. Why not?
Okay, that's the end of our interview with Mr. Ingram. Although I see some people asking about his company in particular, so he's there to he'll be there in the Q&A session in about 15 minutes after our last video, which is from Bruce Anderson. Now, I think I actually say as much in the video that I'm about to show, but Bruce Anderson is with us really as the representative of Generation 3 CSP. So this is the stuff that's over 1,000 degrees. So in that sense, he is perhaps the most unusual and interesting speaker that we have. And it's quite similar to well, I say it's a little bit similar to what Heliogen does, but I think he would actually disagree. And he said, we're not sure about what Heliogen is doing. But anyway, let's go ahead. And thanks for coming on the webinar, Mr. Anderson. So you're in some ways, the most interesting CEO, because you're the guy who has a startup that's looking at the 1,000-degree stuff with the ceramics at the receiver and the heat storage that is sand and using atmospheric pressure, ordinary air as the heat transfer fluid. So it's very different materials. It's a lot more powerful. It's more technically challenging as well. And it's in terms of certain industries that might be interested, it's a temperature that the other CSP simply can't reach. So could you just talk us through your technology?
Yeah, and also it deserves some background too, because I did my master's thesis at MIT quite a number of years ago, and was in the solar industry back in the 80s. And the thing that I came away with above all else from those lessons is that with solar energy, you have to keep it simple. You make it too complicated or you chase too much efficiency and you're in real trouble. So people say, well, with your system here, you're using air. And air doesn't obviously transfer a lot of heat for the amount of volume that you have. And that's definitely the case, but it's air. It's cheap, it's free, and we operate at ambient pressure, atmospheric pressure. There's no high pressure in our system, and all we require is a few blowers and dampers. This is a simple system. Now, granted, it operates at nearly 1,000 degrees, but that's very manageable. I mean, there are a lot of things in the world that operate at very high temperatures, but doesn't mean that that's complicated. It's very simple. And the system is designed with few moving parts. So the way the system works, again, it's fairly simple, is that the cooler air, which is around in the area of 600, that's cooler, goes into the solar receiver on top of that tower. And there it's heated to 1,000 degrees. The heliostats on the ground reflect their light up on top to that receiver. And in the sense that receiver is a heat exchanger, it exchanges, or energy exchanger maybe, it exchanges sunlight to heat and transfers that heat to the air. The air comes out at about 1,000. It goes down to the storage systems there at the bottom. Roughly half go to the storage and roughly half go to the turbine. And then at night, the airflow reverses. The cooler 600 plus air from the from the turbines goes to the storage, and the storage heats it to nearly 1,000 and comes back to the turbine and powers the turbine. Now that turbine is also it's almost miraculous in the sense that we've designed it not to use combustion, but to use atmospheric hot air to create electricity. So there's a lot of exciting developments in this, and we're anxious to bring it to the market.
So for now, it sounds like, this is, I think it's fair to say, the most technologically advanced form of CSP that maybe other people would like to do, but they haven't figured it all out yet in some of the difficult parts, such as the ceramic. But you really, make it clear that it's actually it's simpler in a way than having chemical compounds as the HTF and things like that. And it might end up even, the cheaper option when it has scale, perhaps.
Well, it's our whole idea for this is modularity, which is also true of, for example, Vast, who's on this program, and there are other companies as well who finally figured out that wind and PV and batteries got it right. What you do is standardize a product, you put it all in the factory, and with mass production, you get cost reductions like we've seen, again, with PV, wind, and batteries. Trying to do that with conventional CSP, where they're huge power plants, and they use very sophisticated materials, and like you said, heat transfer fluids like molten salt and HTFs and all kinds of things that really add to the complexity and cost. The whole idea with energy of any kind is cost. You got to get your costs down. And modularity and mass production is the combination that gets costs down.
What is the really difficult part of your thing that sort of prevents others from just hopping on it all at once? Actually, that reminds me of a related question: is to what extent is this purely an American invention right now? Because I really haven't heard of it except from you and Heliogen, and it always seems to come up from Sandia Labs or NREL, other American institutions.
It's actually a globally developed system concept that, frankly, only happens to have occurred in the United States, but it's a global concept. We had a very, very tight collaboration with both the DLR and the Fraunhofer Institute in Germany, for example, on the development of the receiver. And Worley Parsons, which is originally an Australian, as we all know, engineering company, global company, was also instrumental in the design of this system. Saint-Gobain, based in France, is providing the small pieces of ceramic that we're using in this first example here. And for the storage system, we're talking with companies all over the world. So yes, we're based in the United States, but this is absolutely a global design. One more thing about the receiver, and that is that the original receiver concept or collector that sits on top of the tower there is actually a DLR concept that they developed in combination with Fraunhofer. This is a simplified version of that. It's a scaled up version, it's a larger version, but it was developed collaboratively with them as a scaled up version of something that's been proven in the past, but that was originated in Germany.
I think another thing that we could mention is the turbine, the gas turbine. I think it can work with hydrogen, even though it's a non-combustion turbine.
Well, yeah, I failed to mention that. The way we get 24/7 operability and dispatchability without interruption every hour of the year is with the addition of a combustor that we've designed and that we've added outside, external to the turbine. And what that means is that if the air from the storage system or from the collector and the receiver on top of the tower is not hot enough, or it doesn't exist at all, we can burn fuel. And because it's an external, what's called inline duct combustor, instead of buried deep inside of a turbine operating under very high pressure, we have a lot more design engineering latitude. And we can easily modify that combustor to burn almost any liquid or gaseous fuel, whether hydrogen at one end or even diesel at the other, or HFO. We have the it's another aspect of the flexibility of our system to be able to burn almost any liquid or gaseous fuel.
So I guess the next thing, the final thing to cover really is the market opportunities. And I guess I'll dive into a little bit of controversy. I was talking to Craig Wood of Vast Solar, and he was saying, we see that the initial market opportunity is participation on the grid. So I guess the question is, what's the sort of time frame that you see for CSP to start providing industrial heat, either at lower temperatures or at these 1,000-degree temperatures that you think? Because I've said in the reports that it starts to happen in 5 years, but it's still a relatively small fraction compared to, it's sort of on par with hydrogen complexes and microgrids, and then the big one is just mainline grid participation is what I've put in. So what sort of time frame do you see, and what would your route to commercialization be first?
Oh, this isn't going to wait. It's not going to wait 5 years. It's now. Our system, for example, we can provide both heat and power simultaneously, combined heat and power, which is pretty revolutionary in the CSP business. So the way this works is that our module is 400 kilowatts. So it's already industrial scale. And because we use a turbine, that turbine, like all engines, produces heat. And in fact, it produces more kilowatt hours of heat than it does of electricity by their nature. That's just the nature of these turbines, of any turbine, really. And that heat is nominally 250 degrees C. So that's a steady, reliable 24-hour-a-day source of heat for industry, along with reliable 24-hour-a-day source of electricity. So that's now. For 1,000-degree heat, our system can produce that and direct it directly to an industrial process. We don't need to use that heat to produce electricity. We produce that heat at the top of the tower at 1,000 degrees. We think we can go higher in the future, by the way. And we can direct it directly to an industrial process for making cement, steel, glass, other high temperatures requirements. And that's now. We're competitive now.
So how hard is it to pipe the heat? Because you need a factory or whatever it is for the actual industry, and then you need the CSP plant. And it's is it a restriction that they have to be built pretty close together?
They do have to be built close by, but unlike, there's no question about it. You're not going to transport air a long distance, but you can transport steam and liquids at high temperatures. And so there'll be instances where distance is a constraint and a limitation. No two ways about it. And that's probably going to be the biggest challenge is not producing the high temperatures, but to transfer it over longer distances from where the CSP module is located to the point of use.
And I think you're still looking for a big industrial partner or that kind of thing, like Heliogen has recently signed some memorandums of understanding with Rio Tinto and ArcelorMittal, and you're comparable technology to what Heliogen is doing.
We don't know much about what Heliogen is doing. We have we greatly admire their heliostats, which is what they're known for. We know that like other heliostats, they can be used to focus onto our receiver and achieve those 1,000-degree temperatures. But the receiver is really the key, not the heliostats. As I said, there are a lot of heliostat suppliers, but converting sunlight into a high temperature fluid to be used usefully in a process is very, very challenging. And we are not familiar with what Heliogen is doing in that regard.
I know they've mentioned using air, but that's the only thing I've managed to get out of them, which is a bit shifty, I guess. Maybe they feel they've already secured the attention they need. But so where would you expect to start building your first power plants? Would it be California?
We are overwhelmed with interest, and I mean overwhelmed. We are building our first commercial scale system in Arizona in the United States. It'll be fully operational in the first quarter of next year.
Oh, wow.
Meanwhile, we're talking with multiple customers about very, very large power plants to begin deployment next year. And we're talking to literally dozens of customers who are looking to smaller scale systems, even a single module or a few megawatts of our module. This interest is coming from every corner of the world where there's adequate direct normal insolation, DNI. There's no one place that's greater than others. I mean, we're talking about the entire Mediterranean region, North Africa, South Africa, Chile, obviously the United States. We're talking to India, Australia, China. There's a lot of interest in modular CSP today, both because of its multiple applications and because of its cost curve. We see our cost in the future being competitive, literally competitive with PV, but operating 24 hours a day.
Anything you'd like to add? I mean, so anything you think we need to cover?
Yeah, I would say don't underestimate the power of factory-produced modular CSP. It is going to have an enormous impact in reducing carbon emissions, in large part because of its lower costs, but also because of its great versatility and its applicability to solving so many of the challenges to reach zero carbon.
Okay, well, that's the end of our pre-recorded videos. So now we're on to the Q&A session. You may unmute yourselves, Mr. Ingram and Mr. Anderson.
Okay, there we are.
Hello. I mean, before we dive into the questions, is there anything you'd like to challenge from what you've just seen, or that you feel?
No, I think a lot of the comments and a lot of what they said is quite accurate and on spot. And some of it most certainly is technologically oriented, right? So what's true for one technology isn't true for another, and one application the same. So some applications that's great and necessary, and in others it's really a different approach. So I don't have an argument with anything anyone said. I think they're right on spot.
Great. And yourself, Mr. Anderson?
Call me Bruce. No, I thought I was really impressed by the other presentations, and what it speaks to is both the creativity of the human mind, as well as the broad ways in which the sun can be used to solve our problems. There's no lack of imagination, no end to the possibilities, and all these ideas give me hope for the future.
Great. Well, in that case, I'll just get along to the questions. We actually have a fair few. So the first one is from Peter White, who's actually my boss, but he says, is cost the biggest obstacle to the installation of more CSP, or is this only true at low temperatures?
Cost is the issue in energy, period. Obviously, when you're solving additional problems beyond cost, then that factors into what you can charge. But it's unusual to expect to have a large impact on climate and carbon emissions unless you get your costs down.
Anything you'd like to add to that, Mr. Ingram?
Well, I agree. I mean, cost it's the leader in all the problems. But it's not the only problem. And it's kind of, cost is actually a spider with a lot of hairy little legs. So you can look at it in different ways, right? New technologies are not bankable yet. So they might have a great potential cost structure, but they're going to have a hard time getting started until they pass the bankability mark. So yeah, lots of related factors that go along with that. But if you don't have the cost, you don't have a long-term future.
And our next question is from Deep Saxena, and he's asking, what's the monthly average daily solar irradiance for a CSP plant? The only measure I mention in the report is that I think they'll be built almost exclusively above 1,700 kilowatt hours per square meter per year. Do you have any monthly average days of sort of sunny days metric in mind?
Well, let me address that, because obviously DNI is, in a sense, the source of fuel to drive a CSP system. It comes down to economics ultimately. If somebody is paying 25 cents a kilowatt hour and has very poor DNI, you still might be able to make a good business case. On the other hand, if somebody's paying 5 cents a kilowatt hour or less, you could have 3,000 DNI and not be able to make a business case. So there's a trade-off there. Compared with conventional CSP, which can sometimes have heliostats as far as a kilometer, maybe even a kilometer and a half away from the receiver, one of the advantages of modular systems is that you don't have any heliostats very far away from the receiver. They're all very close in a small field. And so you can focus lower quality light, often such as what you find, let's say, on the coast of the UAE or in Florida, where it's a little bit hazy instead of really clear. You can get away with an economic system in those regions if you're modular, simply because you don't get the diffusion of the light. You get as much as you do with the larger systems with the heliostats further away from the tower.
And I think the same idea would apply to a parabolic trough setup, because it's just a trough. There's not so much room for it to get diffused all over the place.
That is true. That is true. And Bruce is right. I echo what he says, but I'll put it another way. Take Germany as a case. You know, they have very high costs, quite poor solar, but their energy costs are quite high. So, you know, what cost is applicable most certainly depends on the local market. So there's always that relationship between market and insulation.
So do you actually see any potential in Germany?
In, you know, parts of Europe, SHIP is very interesting and it's growing. It certainly has a lot of interest. So I don't know.
So it might happen in the future.
It might well happen in the future. Costs keep going up. If you've watched the gas price lately, it's almost at world, you know, historic record highs. So that's certainly going to push solar a bit, solar thermal in particular.
And the next question I have is for Craig Wood, but I happen to know the answer. I asked him the same thing. So the question is from Dr. Kruger, and he says, sodium is a very critical metal. He's referring to the heat transfer fluid that vast solar system uses. And he says any leakage leads to fires and hazards to people in the environment. He says a Japanese battery company had a big accident with sodium batteries at 400 degrees centigrade. And so he's saying, is that a problem? Is sodium a problem? I actually asked a similar question of Craig Wood, and I said, well, sodium just catches fire in the air, doesn't it? And he said, his reply was, we put it inside an argon, I have it noted down somewhere here. He said, we put it inside a blanket of argon, which is an unreactive material. And as long as it stays within the blanket, it's completely safe. And he says, even if it breaks out, then it becomes, you get a fire, but it's less intense at least it's less intense than hydrogen or natural gas, he says. And he said, well, it is a consideration, but we're confident about it. As long as you know what you're doing, it's not a problem. So take what you will from that. I was quite persuaded by his answer, at least. We've got a couple of questions about focal line solar. From Mitchell Williams, I think you already answered that one in the chat. Actually, said you've got some projects in view.
Right, quite a lot of interest. Maybe tracking 15 separate projects in a few regions: Turkey, California, Mexico. Interestingly enough, in Africa as well.
Well, I'm interested to hear about Turkey and Mexico, because Mexico, of course, sort of clamped down on its renewables recently, and Turkey is another place that has a lot that's merely burning fossil fuels, I think. Apologies about my cat, if you can hear that. So Mexico and Turkey are viable as well.
Turkey's viable for some very specific projects, and that's they have a large geothermal resource. To be specific, they have a large geothermal resource, but it's kind of medium temperature stuff. And after operating for over half a decade, they're declining in temperature. Their turbines don't work well in the highest of summer temperatures. So it's a very natural marriage for boosting the temperature with CST. You don't need to bump it much, but adding 20, 30 degrees to it can return the system to 100% operation, or even slightly better, in fact. So, and in Mexico, Mexico, California, water is a serious issue. So desalination is a very interesting target, and there are actually programs for that. So that might be the application, an earlier application as well.
And the next question we have is, John Brinkhurst. He's asking, what's the best hybrid CSP off-grid or mini-grid application for Africa? So it's a wide question, he says.
It is a wide question, and I'm not even sure, we've kind of defined the thing. What's the best mini-grid? Well, are there variants of that?
I think he means what sort of CSP would you do on a mini grid? And I guess it's unfortunate that we don't have Craig Wood here. Perhaps you could email Craig Wood for that sort of question, because he's actually building his project in northeastern Australia, and that's not connected to the main grid yet. So,
right.
We covered it earlier in this webinar, actually. But I'm
going to take a leap and just assume he's talking about what would you hybridize it with, because the CSP part is sort of fixed. So to make up for the off period, the down period, the low, rainy season, whatnot, you have to have something to hybridize it with. And in Africa, I don't think hydrogen is a very good thing. One, the cost. Two, it's a bit more complicated. I think biomass in Africa, of course, depending location, but I think biomass is a great opportunity to hybridize with, and that's what we're looking at.
And we're already seeing photovoltaics plus batteries being a thing for mining in Africa. So yeah, CSP will have a demand there as well. Similarly,
yeah.
So the next question is, we've actually covered most of them in the chat. So if you're watching this and you have a question, please type it now. Otherwise, I have one or two I'd like to ask. But starting with. I think another comment Dr. Kruger posted earlier was about interest from China. He said, well, China is going to be self-contained. It's they have all their own, closed off market where they have all their own stuff. It's all sort of autarkic. But I think one of you, I can't remember which of you it was, mentioned interest from China.
Wasn't me.
Was it you, Mr. Anderson?
Yes. Yeah, there's a lot of interest in China for what we're doing.
And you're the so that kind of ties into another question I had for you, actually, which I think I asked you, but we got sort of sidetracked. I asked you it before, is why aren't the Chinese, and I follow the Chinese news quite closely, so I'm pretty sure they aren't, why aren't they doing their own 1000 degree CSP yet? And are they interested in yours precisely because they don't have their own?
Well, I think, like so many people who've tried conventional CSP, conventional CSP is challenging. I mean, all CSP is challenging, frankly, but it has its challenges. And I think China was discouraged by the outcome of its early efforts in CSP, and so there was a lot of scrambling to figure out what's going to work. Now, the Chinese, to their credit, have kept up their efforts and are making good progress with conventional CSP. But when you've got a serious problem, I think you're always looking for new answers. It's also the case that with a system like ours, that it has so many applications. It's not just to produce power and replace coal plants, which it does, but it is that source of heat. It is combined heating and power. It does provide 1000 centigrade heat. So there's interest in what we're doing everywhere, not just in China.
But perhaps it reflects the still lingering slight technological delay the Chinese have compared to the West, which they've mostly closed in photovoltaics, but I suppose by inertia it's still there in CSP, which is a smaller industry. So perhaps that's why they don't have this 1,000-degree stuff.
Well, I thought, as I said in my presentation, you got to keep it simple, but also doing something, engineering something at 1,000 degrees is not simple. Requires a great deal of effort. We've put $25 million into the development of our technology over a period of more than 7 or 8 years. We got considerable funding support from the Department of Energy. This is hard work. And to our knowledge, nobody else has figured out how to use ambient pressure hot air to drive a turbine to make power without combustion. And without that, our system isn't applicable.
So another question which I remember being asked, and I can't actually see it now, but it was someone asking, how small can you get a CSP project to? And they were asking, what about in the US? Could people have their own CSP projects to heat their domestic pools?
Well, no, they can, but it won't be our system.
It wouldn't. It's a little bit. So single house domestic pool heating is a little bit too small. A little.
You need an absolutely different marketing campaign, an absolutely different company, distribution, maintenance. Everything is different when you start dealing domestic. You're going to have 10,000 customers as opposed to one, industrial scale customer. And it's just a different organization. You can't do both.
It's probably more a thing for solar thermal panels as well. I would imagine.
Well,
traditionally.
Just to be clear, solar pool heating is a 4 or 5 decade old industry. It's happening. You can buy solar pool heaters. This is not a challenge. It's very simple, very cheap, but it's not CSP.
Oh, I think it was you, Mr. Bruce, who told me that the size of your turbines is 200 kilowatts. So is 200 kilowatts the minimum size for you?
Yes, it is. Well, our minimum size CSP is 400 kilowatts because we use 2 turbines, and our receiver is of a certain size. It puts out a certain amount of heat. Our long duration all night storage system is a 200 kilowatt system.
Andries, I think we're past our 1 hour mark.
Oh, right. Well, there is one question I think I should cover before we end it, which is from Javier Duarte. I don't know if I pronounced that right. He says the same capstone turbine that works with CSP hot air. He's asking, could this work with another fuel such as GN or H2? And how would this happen regarding the fuel system? Would it use injectors, WWV, or manifold?
Give him my email, please.
Yes. Yes, I think on that note, I will invite Javier Duarte, or indeed anyone else, to email me, and I can put you in contact with other people. And where's our contacts page? So for questions about the report, you can email me, and also to get in touch with the people I've had on today, because I know their emails. If you want to buy our CSP report, which I certainly hope you want to, email Simon at Rethink Research, and you can also visit our website. So I think, shall I end it there, Peter? I think that's what you're politely telling me.
It was.
Thank you, gentlemen. Thank you, Andreas. Thank you, Peter.
Thank you.